let's look at a simple situation. We've got a train, and on the floor is a laser, and the laser is going to fire photons up toward the ceiling. They're going to hit this mirror, and they're going to be reflected back. Okay? And so it's going to look like this. It's firing a single photon, say, up here, and then that photon comes down like so. And what I want to know is how long is this going to take? How long for a photon to go up, hit the mirror, and then come back down? Okay, so we are going to use just our simple kinematics formula, just basically the definition of speed, v equals d over t. Since we're talking about photons, v is the speed of light. We're assuming we got a vacuum here. And d, it's going up and down, so twice the height of the train car. So that's going to be 2h over delta t. I'm solving for delta t, so delta t equals 2h over c. Okay, nothing spectacular about the result, but there it is. Now, let's look at the situation where we have the train going by and somebody on, next to the tracks, just on the ground there, sees the train go by and sees this photon going up, hitting the mirror and coming back. What would they see? So in this image, I'm trying to show the passage of time. That's what the three train cars are. It's the train at three different moments of time. When the photon's emitted, I should say, then when it strikes the mirror, and then when it comes back. And so we want to know, okay, how long does this take? Well, we're still starting with v equals d over delta t. V, of course, is c. We're talking about the speed of light. But d is no longer 2h because this photon, as viewed by somebody on the ground as the train goes by, this is clearly more than just 2h. Okay, so what is it? Well, let's figure that out. So first off, we've got this distance here, which we already know. This distance is h. Okay. And then we've got this distance here. Now this distance, we don't know what that is, but I do know that it's going to be dependent on the speed of the train. I do know that v, the speed of the train, times delta t, has got to equal that distance, which means that this distance here, which I'm interested in because it gives me a right triangle. Let me make this just a little bigger. There we go, so it's a little more obvious. Okay. This has got to be, whoops. This has got to be 1/2 vt delta t. So that matters, of course, because now I can use the Pythagorean theorem to figure out this side, the hypotenuse. And of course, 2 times the hypotenuse gives me the total distance. So what's the hypotenuse here? Well, that's just going to be, of course, h squared plus 1/4 vt squared delta t squared. That's going to be this side squared. So, of course, I just want that side itself, which means I'm taking the square root, okay, multiplying by 2 because it goes up and then comes down. So there's 2 of these sides, okay? And that is going to be the d I need. All right, so let's put that down over here. So I'm going to have 2 square root of h squared plus 1/4 vt squared delta t squared. And that's all over delta t. Now, the problem here is I want to solve for delta t. That's what I want to solve for, but I have a delta t in the numerator and the denominator and the numerator, and this one is under a square root. Okay, so I'm going to do 2 things. First, I'm going to bring the delta t to the other side, and I'm going to bring the c down over here. And then I'm immediately going to square everything. So I'm going to just skip to that part where I've squared everything. So I no longer have the square root. let's go ahead and distribute the 4 over c squared. That's 4h squared over c squared plus vt squared over c squared delta t squared. Okay. Now I'm going to bring this term over to this side because I'm solving for it. And I'm going to go ahead and factor out the delta t squared. So this is going to become 1 minus vt squared over c squared. Okay. That's going to equal 4h squared over c squared. Okay, now I need to continue my work up on the other side. So continuing to the other side and solving for delta t squared, I'm going to have 4h squared over c squared. Okay. And that's going to be 1 minus vt squared over c squared. Take the square root of everything. And I'm going to get 2h over c. And this is going to be the square root of 1 minus vt squared over c squared. Now, notice this 2h over c. That's the result we got over here. These two expressions are clearly not the same, which means these elapsed times between the two events being the photon being emitted and when it returns to the laser, these two events have different elapsed times between them depending on who's watching. This is time dilation. So what we normally do at this point is I'd come back here and I'd say, okay, this is delta t as viewed from the train. So that's delta t sub t. Okay. This delta t over here is delta ts. So this is delta ts equals delta t times t. And then this whole expression here, excuse me for a second, let me write this in a different color just to make it obvious. 1 over the square root of 1 minus vt squared over c squared, that's commonly referred to as gamma. Okay, so I end up with this relationship, delta t sub t times gamma. And actually, it's usually written the other way. Let me write it again. This is usually written as delta ts equals gamma delta t sub t. Okay, so what I want to point out here, there's several things I want to point out. First off, I want to point out that this is time dilation. This is a big result. It says that the elapsed time between two events is different for different inertial reference frames, or we just say different observers is how we commonly say it. The elapsed time between two events is different for different observers. And this is a huge result from relativity. It's a little bit mind-blowing. And we derived it using very simple ideas. We used the definition of speed. We used geometry, and Pythagorean theorem, a little bit of kinematics here, which actually came from the definition of speed. Okay? So definition of speed, right triangles, Pythagorean theorem. Okay? And we used ultimately the first postulate of relativity, which leads to the second postulate of relativity, the idea that the speed of light must be the same no matter who's looking. So it's the same in all frames. So that's what we used, and we've come up with this mind-blowing result. Now this result I've written in this fashion, but it's normally written like this. And let me write it again in a different color here, something to really stand out. We normally write it like this. Delta t equals gamma delta t naught. So delta t naught is referred to as the proper time, and it's the elapsed time in the proper frame, the elapsed time between the two events. And what defines the proper frame is that the two events must occur at the same location. So the proper frame is the one in which the two events occur at the same location, or you might say the same position. Here are two events where the photon being emitted and then the photon being absorbed, being returning. Okay, and that was here. Both of those happen right here. That makes the train frame the proper frame. So delta t naught, that's the proper time, the elapsed time between the two events as viewed in the proper frame. Delta t is the elapsed time between the two events in any other frame. And gamma is what connects these two. So gamma is right over here, the 1 over the square root of 1 minus v squared over c squared, where v is the speed between the two frames, the velocity between the two frames. So let's talk a little bit about ranges here. Let me scroll down just a little bit to make the room. As I said, gamma is 1 over 1 minus v squared over c squared. The smallest v could be is 0, and in that case, you're going to get 1 over 1. As v increases, you're going to be doing 1 minus some value, and so consequently, this whole thing is going to be a number less than 1. 1 divided by a number less than 1 is greater than 1, so that means gamma is greater than or equal to 1. This defines the range for gamma. Since that's how gamma is, and since we have this relationship here, that means delta t is greater than or equal to delta t naught. And one final thing I want to mention is just with regards to the speeds. Because of gamma, because we so often have this here, v over c, well, v squared over c squared, it will be common to express our speeds in terms of the speed of light. So for example, v equals 0.5 c. And the reason we do this is because that way when I do v squared over c squared, that would be 0.5 squared c squared over c squared, and then the c squareds cancel. So we will often be expressing our speeds in terms of the speed of light. Not always. Sometimes we do need the actual number, but a lot of times the velocities will be expressed in this manner.